Assalamualaikum and good morning. Dr. Majid. My name is Erna. Today I would like to discuss the tutorial dynamic games complete information backward induction. So, the dynamic games are mathematical model of the interaction between two different players, either move sequentially or repeatedly. There is a powerful tool of the analysis, which is an extensive form to check the strategic behavior of the player that interact with each other. There is also the difficulty in deciding the behavior of the player that each action of the player takes at a given time will influence the reaction of the opponent at a later time. Lastly, there is important to understand that an action is a move a player makes at a given point, and a strategy specifies the action that player will take for every contingency. That's all from me. Thank you.
Next, the definition of backward induction. Backward induction is an iterative process of reasoning backward in time from the end of a problem or situation to solve finite extensive form and sequential games and infer a sequence of optimal actions. At each stage of the game backward induction, it determines the optimal strategy of the player who makes the last move in the game. Then the optimal action of the next two last moving player is determined, taking the last player's action as given. And this process continues backward until the best action for every point in time has been determined. Hence, the concept of backwards induction corresponds to the assumption that it is common knowledge that each player will act rationally at each node where he moves, even if his rationality will imply that such a node will not be reached. There is a theorem in backward induction called Zermelo's theorem. It said that every finite game of perfect information has a pure strategy Nash equilibrium that can be derived through backward induction. Moreover, if no player has the same payoffs at any two terminal nodes, then backward induction results in a unique Nash equilibrium. So here is the proof for this theorem. Remark, every finite game of a perfect information has a pure strategy Nash equilibrium. The Zermelo's theorem says that backward induction can be powerful in various finite games. For example, it implies that even a game as complicated as chess is solvable through backward induction. In this sense, in this example, chess is solvable although no one knows what the solution is.
Here's some background about Ernst Zermelo. Ernst Zermelo was born on 27 July 1871 in Berlin, Germany. His parents were Ferdinand Zermelo and Maria Augusta. He was a German logician and mathematician whose work has major implications for the foundation of mathematics. He also known for his role in developing Zermelo-Fraenkel axiomatic set theory and his proof of the well-ordering theorem. He studied at Tree University, and the subjects he studied were quite wide-ranging and included mathematics, physics, and philosophy. In the modern literature on game theory, there are several versions of what is known as Zermelo's theorem. It shown that most of the modern statements of Zermelo's theorem bear only a partial relationship to what Zermelo did. It's generally agreed that first formal theorem in the theory of game was proved by E. Zermelo in an article on chess. In the modern literature on game theory, there are many variant statements of this theorem. Some writers claim that Zermelo showed that chess is determinate. For example, in chess, either white can force a win, or black can force a win, or both sides can force a draw. Thank you.
Here is the example of simple sequential game. We have two players here. Player 1 has the strategy to play left and right, and player 2 has the strategy to play up and down. And this is the payoff for each player. And since this is a sequential game, so player 1 will make the decision first, and then the player 2 will make its decision after the player 1. By the assumption of rationality and maximization, meaning that the player 2 will maximize his payoff in any given situation. So we start from determine the action for player 2. Notice that 3 is larger than 2, so the player 2 here will choose the strategy up. Similar with this, 2 is larger than 1, so player 2 also will choose the strategy up. Then we eliminate the 3, 2 and 3, 1 here. So 1, 3 and 4, 2 are left. Then we compare the payoff for player 1, which is 1 and 4. Obviously 4 is larger than 1, so the player 1 will play the strategy right. The equilibrium for the backward induction is the player 1 choosing right and player 2 choosing up. So we also notice that the result from the previous example is a Nash equilibrium. This is because at each stage of the game, the backward induction will start by maximizing the payoff of players who make the last move in the game. Then the optimal strategy of the next to last moving player is determined until the action in every stage has been determined. Hence, the start game perfect Nash equilibrium is formed as the Nash equilibrium in every subgame is induced.
Hi everyone, it's Azim here. So now I will give an example of backward induction, which is the Stackelberg duopoly. So in the Cournot duopoly, we assume that the firms set the prices simultaneously. There are two firms. The first firm is called the leader and the second firm is called the follower. The leader first chooses its production level Q1. Then, knowing Q1, the follower chooses its production level Q2. So each firm I sells its quantity Qi at the realized market price. P Q1 plus Q2 equals to max 1 minus Q1 plus Q2 0, yielding the payoff of pi I Q1 Q2 equals to Qi P Q1 plus Q2 minus C. Notice that this defines an extensive form game. So at the initial node, firm 1 chooses an action Q1 and the set of allowable action is from 0 to infinity. And after firm 1 chooses its action, firm 2 moves and chooses its action Q2 and also has allowable actions from 0 to infinity. So each of these actions leads to a terminal node at which the payoff vector is pi 1 Q1 Q2 pi 2 Q1 Q2. Notice that a strategy of firm 1 is a real number Q1 from 0 to infinity, and strategy of firm 2 is a function from 0 to infinity to 0 to infinity, which assigns a production level Q2 Q1 to each of Q1. These strategies with utility function ui Q1 Q2 is equals to pi I Q1 Q2 Q1 gives us the normal form. So when we apply backward induction, given that Q1 is less than or equal to 1 minus C, the best production level for the follower is Q star 2 Q1, 1 minus Q1 minus C over 2. So yielding the payoff vector by replacing the moves of firm 2 with the associated payoffs, we obtain a game in which firm 1 chooses a quantity level Q1 which leads to the payoff vector above. In this game, firm 1 maximizes 1 over 2 Q1 bracket 1 minus Q1 minus C, choosing Q star 1 equals to 1 minus C over 2, which is the quantity that it would choose if it were alone.
Hi, here is the example on backward induction with multiple equilibria. We consider the game got two players, which is player 1 and player 2, and this is the payoff for the player and for each strategies get played by the player. And in here we can see to maximize the payoff for player 1, we can see that clearly 0 and 1 is definitely select 1, and 2 and 1 definitely select 2. So we can reduce the games into this one like this. And for player 2 got XYZ 3 strategies to play the game, and to maximize the payoff, definitely the player 2 will choose X and Y, whereas the strategy X payoff is 0 here. So we can let the probability to play X is P, and this one is my 1 minus P and 0 over here. So we can the player 2 can randomly play the strategy X and Y, so the game is the payoff factor associated with the decision of player 2 is reduced to 2p, and the game can reduce into it like this. And the player 1 the strategy selected for player 1 depend on the choice of p, and this is the result for if p greater than 1 over 2 is selected by player 2, player 1 must play A, and if smaller than 1 p is smaller than 1 over 2, player 1 must play D, and if 1 p equals to 1 over 2, player 1 can select any randomization between A and D, and each resulting in different equilibrium. Thank you.
In the given centipede game, there are four smaller games embedded. We call each such embedded game a subgame. As we see, from 2-4 to 3-3 is considered as a subgame. 3-1 to 3-3 is also another subgame. 0-2 to 3-3 is also considered as a subgame. And finally, the entire game is considered as a subgame. The first three subgames we call as the first three subgames, excluding the entire game, we called as proper subgames. In each subgames, the equilibrium computed via backward induction remains to be an equilibrium of the subgame.
I will talk about subgame perfection with imperfect information. In extensive form games with imperfect information, backward induction can be problematic because a player's optimal action depends on which node he is at in his information set. Still, sequential rationality can be captured by the concept of subgame perfection. First, we need to define what is meant by a subgame. In extensive form game tree, a node X is said to initiate a subgame if and only if X and all successors of X are in information sets containing only successors of X. The tree defined by X and its successor is called a subgame. Here is a game with three subgames. Notice that any game is a subgame of itself. Subgames other than the original game itself are called proper subgames. For games of perfect information, every node other than a terminal node defines a subgame. Any subgame is a game in its own right, satisfying all of our rules for game trees. A strategy for the original game also defines a strategy for each of its subgames, sometimes called a continuation strategy.